One of the most exciting aspects of wearable systems is that they bring a technology close to the body and they're with the wearer continuously. This opens up a lot of potential, but also a lot of design considerations. In this section, we'll talk about interacting with on-body systems, how the wearer navigates a wearable system, and what kind of information and communication a wearable system can facilitate. Because wearable systems are close to the body and continuously with the wearer, they have the potential to deliver information more seamlessly than stationary devices or even mobile devices. Displays are the part of a wearable system that shows something to the user. Most of the time when we think about a display, we think about a screen or an image, a visual display. But showing information can be done in any modality, through images, sounds, smells, tastes, or touches. One of the goals of wearable technology is to make information effortlessly accessible. Instead of having to pull out a phone and activate it, in a wearable form, information can be already there, maybe in the peripheral of your attention. Google Glass is an example of something that tries to do this for visual and auditory information. Because the display sits just outside of your gaze, you can quickly glance up at it to take in a very small chunk of information, like what time it is or what the name of the person in front of you is. For visual display, the challenge is to get the display near where your visual receptors are, your eyes. You can see the struggle that Google had in trying to package up a visual display technology that can be mounted on the head. The social aspects of doing this are not insignificant, and I think there's still some development to be done before face-mounted technology is fully socially acceptable. There's a lot more real estate for visual display on other body locations, but it's really hard to see. There's not a lot of space on your own body that you can easily see, particularly when you're not actively trying to look at your own body. The spacesuit tries to get around this problem by putting a mirror on the astronaut's wrist. The dials and controls on the chest of the suit are printed backwards, so that when they're reflected in the mirror, the crew member can read them. This body area may be more useful for visual display to other people, though, instead of to the wearer. Other people can see a lot more of your body than you can. All of the sensory modalities that humans use can be used to display information in a wearable device, but senses like taste and smell are not very commonly used. Auditory displays are very common, but they don't often take clothing-based forms, so we won't spend a lot of time on that modality here. The sense of touch, on the other hand, is extremely interesting for clothing-based devices. In the tactile perception section, we talked more about using the sense of touch to display information to the wearer. If you haven't watched that section yet, I'd recommend that you do so now. As we discussed in that section, tactile display is a really useful modality for spatial information, but there's still some work to be done to develop useful ways of communicating semantic information or language. Some wearable systems are designed only to communicate something from the system to the wearer, so they only include a display. In other cases, the wearable system can communicate something from the wearer to the system, or allow the wearer to control the system. There are a few approaches that try to replicate a keyboard for a wearable environment. This example is the Twiddler chording keyboard. By pressing combinations of keys, the user can type letters or pre-coded words. A drawback is that it has to be held, so it takes up some of the user's capability. This example tries to get around the handheld problem by putting the keyboard in a glove. By touching the spot on the thumb to any of the other spots, the user can type a letter. Both of these use switches for input, similar to what you did when you made open circuits in the electricity exercise. By making and breaking connections in the circuit, the devices are telling a computer or a microcontroller what to do by turning things on and off. There are many ways to make a switch, since it's mostly about opening and closing a connection. One of the challenges of making switches in soft materials, though, is the way that the switch behaves. We're used to getting feedback when we push a button. You can feel it click or hear it click. In a soft switch, it's hard to know if you've actually pushed the button, so people tend to push way harder than they need to, which is tiring and can be really annoying. In the glove here, the designers tried to avoid that by putting a small magnet underneath each contact. That way, when you bring two contacts together, the magnets find each other and they make a little tactile click. Another challenge of wearable input is using small interfaces in different environments. On a laptop, the designers have assumed that you're pretty stationary and that you can put your hands in one position. Designers of wearable systems can't really make that assumption. Their users are probably moving around and doing lots of other things. This example is a control for a group calling feature for snowboarders. Instead of having to use small buttons or touch screens with big gloves on, the users pull tabs and then snap them to make contact points to select modes and to make calls. On-body input devices are particularly challenging because the user often can't see what they're doing, because they're looking somewhere else and none of the body is visible when you're looking straight ahead. Because of this, wearable interfaces have to be gropable. They have to be robust to users feeling around for the right button, or else they risk a lot of false inputs and wrong button presses. This is an example of one approach to making a touch-sensitive interface on a bag strap more gropable. Instead of just touching the right button, the user slides their thumb down the strap until they find the first landing pad. Then they leave their thumb on that pad and reach to the right contact. This gives a little feedback on position, but also triggers the interface to record inputs, so that the user doesn't accidentally push a button by brushing the interface during other movements. In non-electronic garments, fasteners and fastening systems are the interface of the garment. A good interface is easy to use, which requires that the designer consider the ergonomics of using the interface. This applies to both to typically abled people and to people with mobility or dexterity restrictions. Putting openings and fasteners within the reach of the user and orienting them in the direction that the user is strongest helps the usability of the garment. Providing a counterforce for a fastener also helps make it easier to use. Imagine zipping your coat up with one hand, and you'll see why a counterforce is needed. Finally, in both electronic and non-electronic systems, designers need to consider how understandable their system is. How does the user know how to use it? For something like an input device, how does the user know what actions will control what parts of the system? This applies to non-electronic systems as well. Think about the first time you were asked to put on a hospital gown. Were you confused about what side the opening should be on? That's because the design of the gown doesn't provide any indicators of how it's supposed to be oriented.